All right. So let's just start right. I'm going to shout out a number and you tell me what you think where it belongs. Whole numbers are counting numbers. So what about 1? That's a whole number, right? I kind of gave you the clue. What about 2? That's a whole number. What about the square root of 9? Is that a whole number? Okay, well, what is the square root of 9? Yeah, the square root of 9, or I'm sorry, I wrote down the wrong answer. The square root of 9 is 3. Okay, so technically that's a whole number, right? What about 6 over 2? Is that a whole number? What does 6 over 2 reduce down to? 3. So whole numbers are what we call counting numbers. 1, 2, 3, 4. Are those integers? Yeah, because the yellow circle is inside the blue circle. So integers are 1, 2, 3, 4 is an integer, 5 is an integer, 6 is an integer. But integers also have negative signs, yes? Well, the difference is integers can also be negative. Whole numbers are not negative. Okay? Whole numbers are not negative. I would never say I have negative 3 students because I would never count negative 3 students. But we do use negative 3 in math, right? Okay, so whole numbers are counting numbers. That's the easy way to remember it. If I count it, I would never count 3.5 students. I would go 1, 2, 3. Yes?
But isn't 4 and 5 a whole number? So why is it?
Because it's also an integer. Integers are both the positive and negative counting numbers. Huh? What?
It's slow.
Yes. So whole numbers, if you notice, are positive, right? Now, the fancy way to say it is to say that the whole numbers are a set within the integers. If I'll give you an example, you guys are students at River Valley, correct? So if I were to write, maybe we'll go backwards. Maybe that would be more helpful. So let me go over here. We'll talk about it. You guys are students here, right? You guys are students. But you're not the only students here. Some of you are in high school, at least in this building, and some of you guys are in middle school, right? Well, guess what? In middle school, we have seventh graders and we have eighth graders, right? So if you're in the eighth grade, are you in the middle school? Yeah. Notice that the circle right here, the eighth graders, this one right here, is inside the middle school circle. Oh, wait, I did this wrong, though. We got to separate you guys. You didn't make it. Good. Have a seat. So then, if I wanted to do this correctly, sorry, I kind of got excited. So everything on this page is a student here at this district in this building. But in this circle, I have high school students. In this circle, I have middle school. Right? So this will be the 7th graders. This will be the 8th graders. There'd be another circle here for the 6th graders, right? But they're all middle school, and they're all students here at RV, right? Well, the high schoolers, guess what? I got the same thing. I got the 9th graders. I've got the 10th graders. And I've got the 11th graders. Does that kind of help? Does that make a little more sense when I explain it that way? So you could be in the 12th grade, be in the high school, and still be a student at RV. You could be in the 8th grade, still be a middle school student, and still be a student of RV. So you could be all three. But can you guys be 7th graders? No. You're not in that circle. Does that make sense? Yes.
So one, on the other page, one would be a whole numbers. That could be a
Yeah, so if we go back, one is a whole number, but it's also an integer. Yeah, the inner circle means it's a member of both. Okay? Now, rational numbers are integers and whole numbers, but they're also written as fractions. So a rational number could be something like 37 over 4. So it could be a fraction. It could be 3 over 4. It could be negative 5 over 2. Be sure you write this down. Write that down in your notes. Okay? Now, irrational numbers are usually things that are what we call non-terminating, non-repeating numbers, like pi. Pi is approximately, can I get one volunteer to pass out the calculators, please? Yep, come grab them and pass them out real quick. Pi is about 3.14, but does this number stop? No, it goes on forever and it doesn't repeat. So let me show you. And once you get your calculators, you can see this for yourselves. If I plug in pi, this number goes on forever. No, there's no pattern that repeats. In other words, if we keep calculating this decimal goes on forever. And it never repeats and it never stops. Okay? I'll give you another example. If I do the square root of 3, same thing. This number will never stop. It will never terminate. It will never repeat. If I do the square root of 2, it will never stop. It will never repeat. You'll see little miniature patterns, but it'll never repeat. There will never be a pattern where you could draw the line, the bar above the numbers, or the set of numbers. Okay. And by the way, if I put a negative sign in front of it, that doesn't change anything. So if I take the square root, whoops, let me back up this way, and I say negative the square root of 17, same thing. It's a number that the decimal never stops and it never repeats. The fancy math way to say that is non-terminating, non-repeating decimal. Okay? So all of these are what we call irrational numbers. all of these are irrational numbers. So Mr. Adams is going to take a little screenshot of that. Because when I go to do the math, those decimals never repeat and they never stop. Okay? So all of those numbers are irrational numbers. So I'm going to give you a second to write all that stuff down. You don't have to write the decimals all the way out. Just write the stuff here, the square root stuff. I do want you to see why they're rational and irrational and stuff like that. So I did all that to say, because this is example 1. So somewhere on your paper, put example 1. What do you think the square root of 5 is? What set do you think that belongs to? Or sets. It could be in lots of sets. It could be in multiple sets. The square root of 5. What set do you think that belongs in? Yeah, it's an irrational number. So if we're to label that, we would say that that is an irrational number. Well, how do I know that? Well, I could go into the calculator and see if I take the square root of 5. Well, first of all, we know it's not a perfect square. There isn't a number I can multiply by itself to get 5, right? So, but if I plug it in the calculator, I get this crazy wonky thing where the numbers don't repeat and they don't seem to stop. Now, the calculator stops up to so many decimal places, but if I were to do this on a computer, I'll show you. Watch this. If I go here, if I open up a tab, you could do this. Google has a built-in calculator. If I say square root of 5, this just goes on forever and ever and ever and ever. Okay? It goes on forever and ever. This one stops. But watch this. This is the Wikipedia page for the square root of 5. It tells us it's an irrational number. This is the sequence. I'm going to click on this link. Okay. Oops, wrong link. This is the square root of 5. And see those little dots? It just keeps going. So what is the square root of 5? It's kind of hard for you guys to see from your seat. It's 2.23, 606, 79, 774, 99789, 69640. It goes on forever. Nothing repeats, and it never stops. That's why it's so rational. Okay? That makes